In this video, we will learn about the adapter design pattern and how to implement it using C++ code. Adapter is the first of the structural design patterns we'll be learning about in this section. Structural design patterns focus on the relationship between objects and how we can form larger, complex objects from smaller ones. Put simply, the adapter design pattern allows incompatible objects to collaborate. A real-world analogy for the adapter design pattern is a plug. A plug that goes into a USB port of a Windows machine will not fit into the USB-C ports on a Mac machine. However, if we have a USB to USB-C adapter, one end supports USB and the other supports USB-C, making the two compatible. The adapter pattern uses an adapter class to make two objects that were incompatible be able to work together using this class. Now that we understand the concept behind the adapter design pattern, let's learn how to implement it using C++ code. We will start off by creating a class named example1. Inside of this class, we will have an int variable named number that we set equal to 5. Then we will have a public function that returns an int named getNumber, inside of which we will return number. After that, we will have a class named example2. Inside of this class, we will have a string variable named text that we set equal to the string value 3. Then we will have a public function that returns a string named getText, inside of which we return text. Let's create a function that returns an integer named multiply. It will take in two parameters, an int named number1 and an int named number2. Inside of this function, we will return number1 times number2. Notice that the example1 class has the getNumber function, which returns an int, and the example2 class has the getText function, which returns a string. We can't multiply an integer and a string, so our code currently does not make it possible to multiply the value that example1 is storing with the value that example2 is storing with the multiply function. However, we can make these two classes compatible using the adapter design pattern. Let's create a class named adapter that extends the example1 class. Inside of this class, we will have a variable of type example2 named example2. Next, we will have a public function with a void return type named setValue that takes in one parameter of type example2 named value. Inside of this function, we will set example2 equal to value. We will also have a function with an int return type named getTextAsNumber, inside of which we will return a call to the stoi function, which is one of C++'s functions, which allows us to convert a string to an integer. We will pass in example2.getText as an argument into this function. That wraps up our adapter class. Time to test our code. Inside of C++'s main function, we will create a variable of type example1 named ex1. Then we will have a variable of type example2 named ex2. Next, we will have a variable of type adapter named adapter. After that, we will call adapter.setValue and pass in ex2. Then we will output the result of a call to the multiply function and pass in ex1.getNumber as the first argument, and adapter.getTextAsNumber as the second argument. When we run the code, notice that 15 was output, meaning that our code worked. Nice job. In this video, we will learn about the bridge design pattern and how to implement it using C++ code. Bridge is a structural design pattern that allows us to split a large implementation into two separate pieces, the abstraction and the implementation, which can be worked on independently of each other. Let's say we had a triangle class and we wanted to create different color triangles. For each different color, we could create a class like green triangle, blue triangle, red triangle, etc. But as we keep adding colors, our code becomes larger and less maintainable. This is where the bridge design pattern comes in handy. Instead of making a new class for the different colors of triangles, we can add a color property to the existing triangle class that gets specified when a triangle is created. Let's look at how we can implement this pattern using C++ code. First, we will create a class named color. Then we will create the classes green, blue, and red, each of which will extend the color class. After that, we will create a class named shape. Inside of this class, we will have a protected field of type color named color. We will also have a public shape constructor that takes in one parameter of type color named C. Inside of the constructor, we will set color equal to C. Then we will have a class named triangle that extends the shape class. Inside of here, we will specify a public triangle constructor that takes in one parameter of type color named C. Next, we put a colon, reference the shape constructor, and pass in C so that the base class's constructor gets called whenever a new triangle is created. Time to test our code. Inside of C++'s main function, we will create a variable of type green named green, a variable of type red named red, and a variable of type blue named blue. Then we will create a variable of type triangle named green triangle that we set equal to a triangle object with green passed into the constructor. After that, we will create a variable of type triangle named blue triangle that we set equal to a triangle object with blue passed in. Finally, we will create a variable of type triangle named red triangle, which we set equal to a triangle object with red passed into the constructor. Advantages of the bridge design pattern are that it allows us to separate the abstraction from the implementation, create platform-independent applications, allows us to easily introduce new components that can be modified independently from one another, and it follows the single responsibility principle, where each piece of code does one thing and does it well. The disadvantage of using the bridge design pattern is it can make the code more complicated.